Hello, everyone. My name is Joe Perez.
My name is Andre.
My name is Anthony.
My name is Kram.
My name is Mohammed.
My name is Daniel.
We are Group 2, and the project we are presenting today is the cost optimization and design alternatives for structural retaining walls in Chicago Circle Interchange area. The city of Chicago is a metropolitan area which experiences a heavy influx of traffic. To reduce traffic congestion and improve level of service, in 2014, IDOT proposed a restructuring of Chicago Circle Interchange. When analyzing the project as a whole, we noticed about 38% of the budget was geared towards retaining wall 38. Therefore, we did an in-depth analysis to see what alternatives we can take to optimize the cost and design. The result being was redesigning the highest retaining price wall. Furthermore, our EXPO project will be focused on the remodeling of retaining wall 38 to improve the cost value of the project. In these two images, we can see a glimpse of the construction and final product of IDOT's design of the retaining wall 38. The regional geology of retaining wall 38 consists of it being a Wadsworth Lemon formation with a 350-foot thick layer of dolostone bedrock. Furthermore, the soil of this location is composed up to 7 feet of granular and cohesive fill, about 4 feet of medium stiff to very stiff clay crust, up to 40 feet of very soft to medium stiff clay. Additionally, there was water-bearing layers found in the stock pig, dolostone, and granular material. Therefore, we can say that this platform of soil is not good for this design.
The Chicago area soils are known to be poor. They consist of silty clays with low controlling compressive strength value of 0.08 to 1 TSF. The IDOT soil modification plan of improving the soil is by using a 75 feet tall rebar cage, as well as the permanent casing for the two high-mast light towers. You can observe the picture in the bottom. There are 3 other types of soil modification methods that could have been used, which include column aggregate method, fiber compaction method, as well as deep mixing method. By using the IDOT soil modification method is the best one to go with. The existing IDOT wall is a 333-foot long wall with a height of 20.64 feet above the soil surface, with 75 feet deep drill shafts. There are 6 feet in diameter and spaced 10 feet apart from center to center. The benefits of the wall are that it's a fast and easy installation process and it's well known in the working solution.
The 4 proposed solutions are going to be talked about next. The first solution we have is the existing plan view, and with this, we're just going to change the diameter of the drill shafts to 5 feet. The next proposed plan view is going to be the MSC wall. The MSC wall will only run 3/4 the length of the entire wall, and the rest of the wall will be left as the existing wall. Then the last solution that we have is the secant wall. The secant wall will go along the entire length of the existing wall and will replace the wall entirely. To begin, we first have the existing wall analysis, and we can see here that the total cost of the wall based on the IDOT bill of materials and the letting prices came out to be $3 million. Then with the redesigned drill shafts, redesigning to a 5-foot diameter, we can see that the total cost was roughly $2.5 million, and this also takes into account the reinforcement bars with a 20% reduction. Next, we have the MSC wall. The MSC wall is going to run only 3/4 the length of the entire wall. So it's about 228 feet long, the elevation length, with an average height of 20.6 feet tall. And it's also going to have an 8-foot 6-inch wide moment slab. The benefits of an MSC wall is that it's relatively thin, has a flexible design that can carry heavy loads. And it's also fairly expensive though, however, and it's costly and time consuming to construct. And also due to the poor soils, the soil reinforcement will have to extend roughly 100% of the wall height. Looking at the MSC wall cost analysis, one of the items that was taken into consideration was aggregate column ground improvements. And this was determined to be the best solution to reinforce the soils. Similar to our contract 6093, we use similar ground improvements. However, those aggregate columns went 40 feet deep. Due to those soils conditions, with our soil conditions and our engineering judgment that was used, we extended the columns to roughly 60 feet, which led to a higher cost. And our total MSC wall cost ended up being $2.4 million. Our last solution that was was proposed was a secant wall. This will replace the existing wall entirely, so it'll run 317.9 feet along the elevation length with a 20.6 foot average height with 71 feet tall drill shafts. And these are going to be spaced, the drill shafts are going to be spaced 5 feet center to center. The benefits of a secant wall is that it's good for poor soil conditions. However, the disadvantages is that it has an increased cost due to extra reinforcement, and it's difficult to obtain waterproofing. Looking at the secant wall cost analysis, the 4 additional pay items that were needed, the most expensive being the drilled shafts being set in the soil, and the furnished soldier pile. And this increased the wall cost to roughly 3.6 million, leading to being the highest wall cost.
So for the existing IDOT wall design, it consisted of 31 drill shafts that were 50 foot in depth. Then for the shaft conditions, the rebar cage consisted of 24 rebars, and those were number 14. Now for the size of the wall that was already there, it has a height of 21.5 feet. Then the total length of the precast concrete panels is around 333 feet. For the proposed solutions that we had, the first one was to modify the existing drill shafts to cut the diameter. The second option was to cut down the need for drill shafts by installing an MSE wall. The last and third option was to reduce the amount paid for the soil improvements by installing a secant wall. And that would not make us dig that deep.
We use the Brahms method section from the Astro code. The V and M that we calculated in Formula 1 and 2 are the moment and shear of the wall facing. The existing wall has a 6 foot diameter and 10 foot tributary width. The safety factor we used was 4.29. C in Formula 5 is the cohesion of the soil. The caisson length is calculated from Formula 3. We got the unconfined compressive strength QU from the borings. The units were in tons per square foot along the depth. C is equal to 0.5 QU. Brahms method calculation units are in foot, kip foot, and KSF. This is the hand calculation structural analysis for the existing wall. In this slide, we calculate the pressure at the back wall facing by using a rule of thumb, 40 PSF per foot multiplied by the height of the wall, 20 feet, multiplied by the tributary width, 10 feet. From the pressure, we calculate the shear force by multiplying the pressure of the back face of the wall multiplied by half of the wall height. This is our design calculation for our existing wall. The caisson diameter is 6 feet, and we used worst case scenario for the unconfined compressive strength from the borings. Our design caisson length is approximately 50 feet. This is our reduced caisson diameter design calculations for our existing wall. The caisson diameter is 5 feet, and we also use worst case scenario for the unconfined compressive strength from the borings. Our design caisson length is approximately 58.6 feet.
The Excel sheet used to calculate the shaft depths was created by IDOT and had all calculations ready. Some missing components that needed to be added were the moment and shear at the top of the shaft, diameter of the shaft, and layer thicknesses, all of which can be found in the provided IDOT contract 60x95 PDF file. Once all missing information was input into the sheet, it calculated the shaft depths of 50 feet for both walls. The difference between these two sheets are that the diameter used for the existing wall was 6 feet and the secant wall was 3 feet, along with the moment and shear values at the top of the shaft.
So for the MSE wall, we compared it between two aspects. The design aspect was that we found out that we don't need a drill shaft. The second part was that we found out that we need a large backfill area, and that's why the wall only runs from south to north, because we were limited by a very narrow light of way. And then for the cost, we found out that would be cheaper because we don't need any drill shafts.
For the MSC and secant wall drawings, a 3D drafting program called SolidWorks was used. Multiple views such as the front, side, isometric, and isometric exploded were made. This is convenient because it is a good representation of how each wall looks and lets you see the components of the walls and their locations. These are the MSC wall drawings. The front view shows the length and the height of the wall. The side view shows the locations of the moment slab, which is the thick red rectangle on the top, and the straps, which are the rest of the thin red rectangles, as well as the aggregate columns. The isometric view is an angled view of the final wall, and the exploded view makes it easier to see where all the components of the wall go.
This is the hand calculation structural analysis for the secant wall. We use the same format as the existing wall. This is our design calculations for our secant wall. The caisson diameter is 3 feet, and we also use worst case scenario for the unconfined compressive strength from the borings. Our design caisson length is approximately 50 feet.
These are the secant wall drawings. This model does not show the entire length of the wall since it's a lot bigger than the MSE wall because of the long shafts. To keep the drawings at a reasonable and readable scale, we only made an 80-foot section of the wall. The secant wall shafts are much closer together than the existing wall. Because of this, there are only 31 shafts on the existing wall compared to the 61 shafts on the secant wall. The front view displays the depths of the shaft as well as the spacing between the piles, and the side view shows the heights along with the diameter. Just like for the MSE wall, an isometric and isometric exploded view are shown. The exploded view has a similar layout to the MSE wall. The main difference is the soldier piles and the secondary shafts.
Looking at the cost optimization and the total of all the costs, we can see that the MSC wall totaled out to be the cheapest at 2.4 million.
In essence, based on our analysis, the secant wall will be the most costly due to the materials and shaft presence. The MSC wall will be the most cost-effective due to the number of shafts used, while the original wall will be the best optimal project to be used due to the soil present and scheduling needed for the project.
These are the references and acknowledgements we used.
Thank you for your watching.
Thank you.
Thank you, everybody.
Thanks, guys.